First let's just do it and then see what it means. Okay, so I'm going to suggest, so how many parameters are there and how many variables are there in this problem? S, okay, S0, U, T, G. There are 5 things, right? Suppose you did not know this equation, or you want to represent this equation but as a data set, okay, not as an equation. What would you do? Your interest is to prescribe the location of the particle as a function of time. So if you were to plot a graph, you will actually plot S versus T, right? You will plot S versus T as a graph, but then you have to tell for what value of S0, what value of U and what value of G you would be plotting it. The moment you change S0, U and G, the plots are going to be different. Agreed? So you can say T is your independent variable, S is your dependent variable, and S0, U and G are parameters in the problem. Okay, the moment you change the parameters, you are going to get different plots. So this may be for a given set of parameters S0, U and G. Okay, let's say 0, 1, U1, G1. You might get it for S0, 2, U2, G2 and so on. For each of them you are going to get different plots. Okay, or if you were to do experiments without you knowing this relation, you would have changed S0, G and U multiple times to get these plots. Okay, so you have got in this particular problem 5 really variables, out of which you have identified a dependent variable and an independent variable and 3 parameters. Okay, out of which I will say we will select 2 scaling parameters. Select 2 scaling parameters. Now what is meant by scaling parameters is essentially you are going to use that scaling parameter to non-dimensionalize your other variables. So remember, when we were doing the pipe flow, we non-dimensionalized our equation in some fashion. We chose a characteristic length, we chose a characteristic velocity. Okay, similarly you are going to select certain things and then you are going to use that to non-dimensionalize your equation. So here, so we don't know how many we should have actually chosen. At the moment, let's not worry. I'm just telling you that let's select 2 of them. So in this case, I have S0, U and G as the parameters. We have to select 2 of them. So let's say in case 1, select S0 and we used U as the scaling parameters. Okay, so that means I'll define my S star is equal to S divided by S0. Okay, I have one variable. I need to define my T star, which will be, how can I generate a non-dimensional time from S0 and U? S0 by U. S0 by U basically has the dimensions of time. So I can non-dimensionalize my variables. I have gotten a non-dimensional S star and a non-dimensional distance and a non-dimensional time. So our original equation was S is equal to S0 plus UT plus half GT square. I try to non-dimensionalize this equation by substituting S is equal to S0 S star is equal to S0 plus U into T will be T star times S0 by U plus half G. T square is T star into S0 by U whole square, or taking away my S0 from all of them, one of them there. So basically I end up with S star is equal to 1 plus you will go T star plus half G S0 by U square times T star. And let me call this parameter, say some alpha. So that means S star equal to 1 plus T star plus half alpha T star square. Right? Oops. That's the equation that you are ending up with. Right? So alpha has come out as a non-dimensional parameter for you. Is alpha dimensional or non-dimensional? It is G times S0 divided by U square. Okay, so that has no dimension. So that is the non-dimensional parameter that is actually characterizing this equation. In which case you would have been able to just plot S star as a function of T star for just one parameter alpha. Okay, that tells you what the curve is. You don't have to worry about three different parameters now. So you have actually simplified your description. Agreed? Okay, now we have been able to do this because we selected two scaling parameters, right? So what did we do? We selected two scaling parameters. One was S0, other was U, and then we non-dimensionalize the equation. Let's say you are going to select a second case, case 2, select U and G as the scaling parameters. So how can we do that? We can define, so we have got U which has the dimensions of length per time and G which has the dimensions of length per time square. So we can define, let's say S double star is equal to S divided by, how can I create length out of this? U square by G. U square by G, and I want to create a time out of it. U by G. Okay, now can you non-dimensionalize and tell me what is the relation S double star you are getting as? S double star equal to G by U square. There should be something more. S0 was originally there, no? It's there, plus correct. Okay, so this parameter is what we had originally defined, identified as alpha, right? So we have really gotten S double star is equal to alpha plus T double star plus half T star square. Okay, again we have got a non-dimensional equation, okay, which is again parameterized only by that parameter alpha. Okay, though it appeared differently because we have now scaled it differently. We have chosen different set of scaling parameters. Okay, we will do one more and then we will conclude. Case 3, select, what are the ones which are left out now? Select S0 and G, I think. We didn't do that combination, right? As scaling parameters. That means if I define a non-dimensional parameter S triple star is going to be S divided by S0, T triple star is going to be T divided by Abu Sai Kumar. Abu Sai Kumar. What non-dimensional parameter, what time scale would I choose to non-dimensionalize? So I am using S0 and G, okay, to scale. You mean S0 square by G, that will have the dimension of so this is meter square, this is meter per second square, so this will have the dimensions of second square times square, so you need that, right? Go ahead and non-dimensionalize. Yeah. What is that? Root S naught by G. Yeah, that's also fine. No? So root S naught. What is meant by root S naught? Root of S. Correct. Oops. Now write. Sarin John, yeah, can you tell? 1 plus u by O under root G S naught. And this is 1 by root alpha. Okay, so again we have been able to get it. Okay, in all cases, so in the first case we found S star is a function of T star comma alpha. The second case we found S double star as a function of T double star comma alpha. Third case we found S triple star as a function of T triple star comma alpha. Okay, so alpha is the parameter that has always come out in some form, okay, and therefore alpha is the only non-dimensional parameter that's in the problem. It doesn't matter which scaling parameters you select, you will always end up with that parameter, the right non-dimensional parameter. It may just come out in a different form. In fact, if you look at in the first case, okay, we had, where did alpha appear in the first case? In the first case, it was really S star is equal to 1 plus T star plus half alpha G T star square. So alpha was coming in the place of gravity. Okay, so you really can think about when you are changing alpha there, you are really changing your gravity. So you can really say that, okay, so there alpha really represented how, if I were to change gravity, what would have happened. That's the physical interpretation that would have come out. On the other hand, in the second case, alpha came out at the place of the initial displacement. So alpha was really playing the role of initial displacement. In the third case, it would have come out as the initial velocity, u. Okay, so you could interpret that non-dimensional parameter in any fashion you like, because alpha always contained these three things, G, S0 and u. Okay, and you can actually interpret it in multiple ways. And that's because it's essentially a non-dimensional quantity. So how did we define alpha? Alpha was defined as G S0 divided by u square, no? Or is the other way that we defined? This way, right? So this contains G S0 and u square. So I could write this as G divided by SU square divided by S0. In that sense, we are saying, oh, it's gravity to some other acceleration in the system. Or I could have written it as G by u square divided by S0 inverse. Then I would say that, oh, okay, or maybe I should do 1 by alpha. Let's see here, 1 by alpha, I'll write it as u square divided by g s0. So there it would carry the meaning of some velocity square by some other velocity square. So all non-dimensional numbers you will be able to interpret it in multiple ways. Okay, whether you want to interpret it as strength of gravity, whether you want to interpret it as strength of the displacement, anything. Okay, and what this exercise has shown you is that it doesn't matter what the scaling parameters that you select, you will always end up with the right expression. In all these cases, we ended up with right expression even though the precise form of the equation was different in each cases. Okay, so non-dimensionalization will not be able to tell you what the precise form is, it will only tell you what are the relevant parameters involved. Is that clear? Okay. Any questions? Should I repeat anything? Yeah. Depending upon what you want to do it, right? If you are worried about flow here, then you don't have to care about. But if you are worried about flow between what is happening at equator and what is happening at pole, you might. Or you want to talk about what is happening in, moon and what is happening here, you want to talk about, right? So that's why. So you want to call it a dimensional constant or a dimensional variable depending upon your problem. So you look at this. The simple equation has now actually told you everything that you have to know really about non-dimensional analysis. Okay, except that we just don't know, given a situation, how to do that. Okay, so that's our next goal. I'll just say a few things and then we will stop and we'll do the rest in the next class. Power law expression. Given any physical quantity, okay, any physical quantity, if you look at its dimension, so we only worry about, let's say, fluids and fluid flow. Any parameter that you are going to look at, let's say x, its dimensions will have the form of L to the power of alpha, m to the power of beta, t to the power of gamma, where L, m are length, mass and time, the fundamental dimensions that we have chosen. Is that always true for any of the properties or any of the variables, any of the physical quantities that you are familiar with? You're agreeing or disagreeing? I'm confused. You want to say something? Go ahead. So if you want temperature, you want to include that. I'm going to worry about things that are relevant for flow. Heat transfer, will keep it aside. Always worry about constant temperature. Right? But how do we know whether it's always correct? We know that this is what we have always observed. Right? Velocity, length, mass, force, power, work. Right? So we are going to prove that this is always going to be the case, from which we will derive something called Buckingham pi theorem. Have you done Buckingham pi theorem? No. Okay, so we will derive that, and that is the theorem that we are going to use to get non-dimensional equations, which we will do next class.